Welcome back, everyone. In this video, I'm going to provide you with a few extra practice problems that you can work through, and then I'll show you a solution to them. These test your ability to identify reactions by their reaction type, balance chemical reactions, use the solubility guidelines, and write out molecular equations, full ionic equations, and net ionic equations. Okay, so for this one, you need to balance each reaction, then classify and determine the driving force for each one. So pause the video and try this on your own. Welcome back. So let's go through and do these. So in order to balance the reactions, we need to make sure that we have the proper number of each element on each side. So one way that you can do this is by writing out each of the elements and starting to identify how many there are of each. We have 2 sodiums on the left, 1 sodium on the right, 1 sulfur on the left, 1 sulfur on the right, 1 hydrogen on the left, 2 on the right, and then 1 chloride each. So let's start by looking at our sodium. When you're balancing chemical equations, it doesn't matter which elements you start with, so long as they only show up in one location on either side. So the fact that sodium is only in one reactant means that we could start with that. So we know we have 2 sodiums in our reactants, so we need 2 sodiums on our products. That now has changed the number of chlorides as well. So let's go back now and adjust our chloride count. We have 2 chlorides on the left, or on the right, 2 on the left now. And now we've changed our hydrogens. So now we have 2 hydrogens on the left and 2 hydrogens on the right. Everything's balanced. For reaction number 2, notice that if we try to balance this with oxygen, it would be a nasty mess. So let's start with a different element. We've got carbon, oxygen, and hydrogen involved. So we have 4 carbons on the left. Now we can have 4 on the right. Okay. Again, let's leave oxygen until the very end because it shows up in a lot of different places. We have 8 hydrogens on the left and 2 on the right, so put a coefficient of 4. Now we have 8 and 8. And now let's count up for oxygens. On the left, we have 4 oxygens, and on the right, we have 4 plus 8 is 12. So we need to modify the coefficient in front of the oxygen molecule. So we need 8 more oxygens. So if you put a coefficient of 4, now we have, let's see here. Oh, not quite enough. So again, here we have 2, and now we have 8. That adds up to be 10. So instead, we need 5. At that point, we have 2 oxygens from the hydrocarbon, and then 10 from the oxygen molecule, and that's a total of 12, and then 8 there, and 4 there, total of 12. Okay, this third reaction. So we've got nitrogens to balance, hydrogens, and oxygens. Let's start with the nitrogens. We have 2 nitrogens on the left, 2 nitrogens on the right, so that's balanced. If we do oxygens, notice we have oxygen in 2 different places in our products. Not good to start to continue there. So let's go back, look at hydrogen. We have 4 hydrogen in our reactants, so we need to put a coefficient of 2. That means now we have 4 and 4, so those are balanced. Now oxygens. We have 1, 2, 3, or 2 oxygens plus another 2 here, so we have 4 oxygens on the right, but only 3 on the left. This is going to be a little bit harder to balance. One thing we could do is if we put a 1/2 here, that's going to reduce this down to 3. Now, we don't normally like to have halves in our reactions, however. So if we multiply the entire reaction by 2, then that will get us all whole numbers. So if we do that, we have 2 of the ammonium nitrate, 2 nitrogen, 1 oxygen, and 4 water. Let's double check now our numbers. We have 1, 2, 3, 4 nitrogen, 4 nitrogen. 8 hydrogen on the left, 8 hydrogen on the right, 6 oxygen on the left, 1, 2, 1, 2, 3, 4, 6 oxygen on the right, and we're balanced. Okay, here we have just nitrogen and hydrogen. So let's start by balancing the nitrogen. Now we've got 2 nitrogen on the right and 2 on the left. We have 6 hydrogen on the right, and so we need to have a coefficient of 3 there, and so we have 6 and 6. All right, so we're all balanced. What are the reaction types here? This is, we see here, this is a double displacement. And it's driven by the formation of a gas. We know it's double displacement because our reactants are each, we have a pair of cation and anion in both. The second one, we're taking a substance reacting with oxygen to form carbon dioxide and water. You should recognize this as a combustion. And here, there's actually multiple driving forces. We have the formation of a gas. This is also a redox reaction. For the third, we see we're taking one substance and forming multiple others. So this is a decomposition. And we have here the formation of a gas as our driving force. And then here as well, this is a combination. And this one's a little bit harder to tell. We'll talk more about it later, but this one is actually a redox reaction. Don't worry so much about classifying these as redox reactions yet, because we haven't talked about that quite yet. All right, here's another problem. Work through this one on your own and then come back and I will share with you a solution. So we want to know what's the net ionic reaction when silver nitrate reacts with sodium chloride in aqueous solution. The first step is to write out the balanced molecular equation. We have our reactants, and we know that since each of them have a cation and an anion, that we're going to do a double displacement. So we swap the positions of our cations and we have silver chloride with sodium nitrate. Now, using the solubility rules, you should be able to predict that silver chloride would be solid or insoluble, but sodium nitrate would be soluble or aqueous. It is balanced in terms of the charges and the numbers. Our complete ionic equation is where now we want to write out anything that is a strong electrolyte and soluble. So anything that is aqueous will be a strong electrolyte if it's a strong acid, a strong base, or if it's a salt. So we have silver nitrate, which is a salt, sodium chloride, which is a salt. Any solids, liquids or gases, are non-electrolytes, so they don't dissociate in water. And then sodium nitrate is also an aqueous salt. Our net ionic equation we can find by eliminating any spectators, the elements that appear in the same way on both reactant and product side, and then rewrite our net ionic equation. All right, here is one more, and the final question of this video. Pause and try and determine this on your own. Welcome back. So we want to identify what's the net ionic equation for the reaction of sodium fluoride mixed with hydrochloric acid. Let's start by writing out the equation. What do we have that's going on here? Well, we actually have the formation of a weak acid as the driving force. And we can identify this because with our molecular equation, we have our reactants, hydrochloric acid and sodium fluoride, and those are we'll do a double displacement. We can predict that because each of them have a cation and an anion, and they're an aqueous solution. So we end up with sodium chloride and hydrofluoric acid. Hydrofluoric acid is a weak acid. Therefore, the reaction for this is the formation of a weak electrolyte. The complete ionic equation with the spectator ions, we see that we would eliminate chloride and sodium ions. Notice here that we don't dissociate the hydrofluoric acid. That's even though it is aqueous. The reason for that is because it's a weak electrolyte. It's a weak acid. Any weak acids or weak bases we show in their undissociated form in the ionic equations. So that means then our net ionic equation is going to have hydrogen ion plus fluoride ion forming hydrogen fluoride aqueous. That's it for this video. Thanks for watching. Have a great day.